This is the second talk of my series, and I called it Spectrum of Singularity and Homological Blocks, because this is what I will talk about today. So, okay, this doesn't. It works. Okay, so first I will tell you some background, then I'll tell you something about homological blocks, and finally something about the spectra. So, let me recall from the last time. Steam ring spectrum, or Arnold-Varchenko steam ring spectrum, is an analytic invariant of an isolated hypersurface singularity which satisfies strong properties. I told you it satisfies this Thom-Sebastiani property, semi-continuity, etc. Yeah, and also I wrote here isolated, but it can be generalized to many other cases. So this is an example from the previous. So if we have a singularity x squared plus y cubed plus z5, which is called E8 singularity, then the spectrum is 8 numbers, and I write here the common denominator like this. So they are all 1 over 30 and etc. So this is an example. Okay, and now this time it will be all about surface singularities. So it means we will have 3 variables like here. So for surface singularities we can construct a corresponding link. I mean, we can construct link for any singularity, but for surface we will get a 3 manifold. So we have this singular point, isolated one. It's hypersurface, so it sits in C3, and this has real dimension 4, right? Because it's a complex hypersurface. So if we intersect with S5, then we will get something here, and so the dimension is like, you know, the codimension is the codimension of this plus codimension of this, so it will be a 3 manifold. So we get a 3 manifold. Okay, so this is what we call link of singularity, and so the question is like how much of the analytic properties of the singularity can be recovered from the link. So this is an old question studied by many people. Yeah, and so the topic of this talk will be some very like sophisticated 3-manifold invariants. So this Witten-Reshetikhin-Turev invariants and so-called homological blocks, which is kind of like a refined version of these Witten-Reshetikhin-Turev invariants. So we can ask like, do these like 3-manifold invariants tell us something about the singularity? Because there are like so for example there is this Casson invariant which we learned last time that it's related to this so the numbers of spectra at some intervals of this signature of the intersection form. So there are many relations like this, but those invariants are kind of new, so we can ask if they have something to do with the singularity. Okay. So yeah, so just like to recall this definition, so if we have a compact oriented 3-manifold, it's a homology sphere if the homology is the same as the homology of 3-sphere, and it's a Q-homology sphere if it works over rationals. So that means that there can be, so yeah, an example. So if we take any ADE singularity, so those are simple singularities which are assigned to ADE Dynkin diagrams, then the links are all Q-homology spheres, and only the link of E8 is a homology sphere, and this is an important example for us. So this is this Poincare homology sphere. Okay, so Q-homology spheres have some non-trivial torsion in H1. That's the only thing which differs from like homology spheres. So we have this first homology, which must be a finite group. Otherwise, this wouldn't be true. Yeah. So this finite group, we call it H, and it plays an important role because, so on the topological side, it labels the abelian connections like U1 connections, and also the spin C structures, and also the homological blocks, which I will talk about. And on the like analytic side on the side of singularity, it is a covering group of the universal abelian cover, which I'll talk about too. So this is those are two like things where it plays an important role. Also, there is a like a bilinear form or quadratic form on this group, which is also important. It's called linking pairing. Okay. So let's talk about let's see the example of Poincare sphere. So it's a link of the singularity, as I told you. So we have that the pi1, the first fundamental group of this manifold, has 120 elements. So it means that it is not diffeomorphic to S3. And we can, I mean, we can study other invariants, because this is like kind of very simple example. So we can study these Chern-Simons invariants, or this Witten-Reshetikhin-Turaev, which is like kind of more complicated version of Chern-Simons. So now we consider these two functions. So I write here tau is the variable and q is like exp of 2 pi I tau. This is like from the theory of modular forms. You always this like substitution. So we write these two functions, which are some q series, some infinite series in q. I don't write all the terms here, so you cannot know what is it. But so there are these numbers like these violet numbers, which are actually the Chern-Simons invariants of these three manifold. And this theta plus is related to this Witten-Reshetikhin-Turaev. I'm sorry that I won't define it for you, but yeah, this is like the work of Lawrence and Zagier from, I think, 1999 or 8. So if we make so-called Eichler integral of theta plus, you don't have to worry about what is it, but it's just some like we do something with this first function, then we get a q series which converges inside the unit disk. And if we do radial limit, so we get like a function which lives in the unit disk, and if we do radial limits like this to roots of unity, then we get these invariants, these Witten-Reshetikhin-Turaev invariants of these three manifold. So this is a famous theorem which kind of like brings to classical like topology the theory of modular forms, because those are some modular forms. Yeah, and so now when I saw this paper, I was wondering if like there is like maybe there could be a relation to the spectrum. So I looked at the numbers, and so here it is. Okay, so this number 30 is in this denominator, because we have 1 over 4 times 30, and these four numbers you can see 1, 11, 19, 29. So they're here, and the blue numbers are there too. Okay, so yeah, the important point is that like these Witten-Reshetikhin-Turaev invariants are really related just to this first function. What is the meaning of the second function? So the meaning of the second function is that this first function is not a modular form for the full SL2Z group, but together as a vector with the second function, it forms a modular form, vector-valued modular form for SL2Z. So this is like kind of invention of Lawrence and Zagier, that they found this second function. Yeah, and so we kind of see that if we take both of them and we look at the first coefficients, we have like the spectrum. Okay, so yeah, I mean, of course you may ask like what are the other coefficients, and yeah, so this is like a first clue that there could be like some relation. So so now I will tell you something about these functions. So definition, so weight 3 halves, unary theta function is defined like this. So we take sum over a residue class modulo 2m, and we take L times Q L squared over 4m. So you see there is this 4m, so m is 30, and there are these residue classes playing a role. So those theta functions, there is 2m of them because you have 2m residue classes. Okay, yeah, I can actually use this. Okay, so 2m residue classes, and these functions form a rank 2m because there is 2m of them, vector-valued modular form of weight 3 halves. So that means that like if you substitute like -1 over tau or like tau plus 1, then you get like a transformation formula. So you can express this like theta of tau plus 1 as a vector in terms of some like in terms of these original theta functions multiplied by some 2m times 2m matrix. So you have these S and 2 matrices, which you can write explicitly. I will show you then an example. And these define the so-called Weyl representation of the like double cover of SL2Z, because so in the usual classical theory of modular forms you have SL2Z, but here we have this half. Yeah, it's 3 half theta function. So there is some factor like some rational power like of the variable. So you need to go to the double cover okay. So and then I want to define this Eichler integral. So the Eichler integral is just that we take a similar sum. Now we don't have this L, we only have like a sine of L, and so this is this function. So it's clearly somehow related to this function, but it does not have this modular property like this vector. It only satisfies some weaker modular property, which is what Zagier calls quantum modular forms. Yeah, or you can hear like mock modular forms, false theta functions, because this is just taking like a half of the infinite sum. So yeah, so this is so why I'm talking about this. So this is here. Yeah, so those are these theta functions, and you have to go to this Eichler integral to get these WRT invariants. Okay. So you have to like trade your modular properties for weaker ones to get these invariants. And it's a good question whether like for example this second series is also a 3-manifold invariant, yeah, or like if it has some geometric meaning. So this is what we are asking here. Okay, so once again Poincare sphere. So we have this example. So this theta plus and theta minus, which was sorry, I'm going the other way, which was here. So now I will give you the full expression. So they are written as linear combinations of these unary theta functions. So it goes like this. Yeah. So you have this 1, 11, 19, 29, and then these negative terms, and here you have 7, 13, 17, 23. You can notice that this number is always like 60 minus this thing. This one is like 60 minus 11, 60 minus 41. So there is somehow there is kind of symmetry in this. So yeah. Yeah, sorry, that's just a mistake. Yeah, it's the same function. Yeah. So and I told you that you have like, so this is like a modular form for SL2Z. So what are the T and S? What is the representation corresponding to this? So the T is just a diagonal matrix with some root of unity, e to 2 pi I over 60, and S is just some matrix. I'm not sure if maybe I forgot some overall factor, but it's just some like a very explicit matrix, and you can write it for many other examples. So these are the theta functions of Poincare sphere. So now I'll talk about something completely different. So if we have a isolated surface singularity. So we only take the germ, so it means we only take like a neighborhood of this singular point as a topological space, and then we suppose that the link of this singularity is Q-homology sphere. So this is kind of in all examples we consider, and it's really important. So it means that we have this finite group H1 of the link H, and we can consider the maximal unramified abelian cover of this neighborhood without the point. And finally, so we go to covering and we add one point so that it's again another singular surface or germ of a singularity. So this is called, this is called like universal abelian cover. Oh, I didn't write it here. So this was studied by Neumann and others, and the important theorem, which was later generalized, talks about quasi-homogeneous singularities. So quasi-homogeneous singularities, I mentioned it last time. Those are such that you can assign some weights to variables, such that each of the monomials in the in your polynomial have the same overall degree. So if you have a germ of an isolated quasi-homogeneous singularity such that the link is a Q-homology sphere, then the universal abelian cover, which I call Y and Q is the point, of XP is a Brieskorn complete intersection singularity. So what does it mean? So Brieskorn complete intersection, this is just like something which looks like this x to the P1 plus x to the P2 plus x to the P3. Yeah, but in general there can be like more variables, and there can be more equations, so that you get like complete intersection singularity instead of hypersurface singularity. But it always has this like very simple diagonal form. Those don't have to be coprime. So so this is the theorem of Neumann, and then lately he has like some conjecture that you actually don't need this quasi-homogeneous. You can do it much more generally, which is kind of surprising because those singularities, they can be very complicated. They don't have to be complete intersections. Yeah, they can be really like have many equations, and you always get this like complete intersection, which is kind of surprising. There is no reason. But for us, it's very nice because even though we are very bad in computing spectra for like ugly singularities which are not complete intersections, we can always compute. It's much better to compute like these Brieskorn type complete intersections because those are kind of simple singularities. So it's much easier to compute the spectrum using this Tom Sebastiani theorem. Okay. So example. So the E7 singularity can be written like this. So we have this, if we set this equals 0, we get a singular surface with one E7 singularity. And so topologically, the link is can be written like this. So the meaning of this is, so this is like a manifold given, so this is a Seifert manifold given by Seifert invariants. So this is like so it's a fibration over S2 with 3 singular fibers, like S1 fibration, and those numbers encode the information about the singular fibers. So this is like one way how to see this, like from kind of in a different way, is that you have this. So if you resolve the E7 singularity, you have this E7 linking diagram, right? Like 1, 2, 3, 4, 5, 6, 7. Oh, sorry, I'm doing something else. Let's see, here and here, right? And the same thing happens. So this is the resolution. So you have -2 curves which intersect in this pattern, and the same graph gives you the plumbing construction of this link. So you have some surgery construction which gives you this link, and those numbers you can get them like some from this diagram using continuous fractions. So like this corresponds this leg corresponds to this 1/2, this one corresponds to this 2/3, and this one corresponds to this 3/4. Okay, and so the important numbers are for here are these denominators, because this is the only information which we need to get the abelian cover. According to the Neumann theorem, he gives the equations. Yeah, so the equation of the abelian cover is just x squared plus y cubed plus z4. So yeah, so it tells us that we really use just the topology, and we don't even use the complete topological picture. We just use these like denominators. Okay, so we for example we ignore this linking pairing on this H1. Yeah, so the abelian cover of E7 singularity is this equation, which gives you E6 singularity. Similarly, if you start with E6, you get D4. If you start with D, you get A, etc. And if you start with E8, you get E8, because this H1 is trivial. So it's already like its own universal abelian cover. Okay, so these are the abelian covers. Are there any questions?
In the previous slide, what is this -1, m -1?
Yeah. Okay. So this is just like yeah. So this is just like some normalization of the yeah. So there is like many. So there is like many ways how to draw this diagram, and one of them would be like -1. And you would have here like these like numbers like -2, -3, -4. And if you do this like Kirby moves, you get here -2. But yeah, there are many, there are like many ways how to write those numbers, and there are some transformations rule. You can add like +1 here and subtract -1 here, yeah, and stuff like this. So yeah, that's the meaning. So it just if you write it like this should be rated by this Kirby moves, like different ways how to change the surgery. Yeah, or like so yeah, the -1 is here. Okay.
So I mean,
yeah.
Can I ask one more question? So I mean,
yeah.
Anyway, I don't know much about these things, but there may be some other way of surgery to make string. Right?
That's true, but these three numbers, they're always the same. They don't change. Yeah, that's like an invariant of yeah. They're like yeah.
I mean, whatever surgery I made, I should.
Yeah. Those are invariants of the three manifolds. This 2, 3, 4. Yeah, for E8 you get 2, 3, 5. E6 you get 2, 3, 3. So yeah. So whatever. I mean, there are many ways how to write this, but those denominators are always the same. Okay, so now I will just like say quickly something about the history of these three manifold invariants. So it started with, I mean, as far as I know, it started with Witten and his Chern-Simons path integral. So you have this like you can study abelian non-abelian SU2 connections on your three manifold. So you basically study like vector bundles or yeah, and so you can kind of like try to, so you can compute this Chern-Simons invariant, so you get like a discrete numbers for your flat connections. But you can also, like in quantum theory, you want to integrate over all connections, not just flat ones here, because the flat, they corresponds to like your solutions of equations of motion. So he constructed this like path integral. And then in 91, Reshetikhin and Turaev, they gave like a mathematical definition of the same thing, yeah, or at least it's believed that it's the same thing, because it's kind of hard to define this properly. So this is the definition of this WRT, which depends on an integer n, and it's been defined by exactly like by this surgery procedure, yeah. So using the representations of quantum groups. Then in 1999, I told you this result of Lawrence and Zagier, that for one particular example, this WRTN can be computed as a radial limit of some Q series. Yeah, and they also gave some like idea how to generalize, but it took a while to generalize. So then Kazuhiro Hikami, Japanese mathematician, he wrote like many papers on this topic. So in 2006, he gave this conjecture that for Q homology spheres. Okay, so this is all topology. There are no singularities. Yeah. So for Q homology spheres, this Q series, which you get like such the one which gives you WRT, can be decomposed into like a combination of some more refined Q series with algebraic coefficients labeled by these elements of this H group, and the linking pairing plays an important role there. Like yeah, so there should be some like more refined invariants, and they have algebraic coefficients. And so this kind of doesn't happen for this case E8 because it's just homology sphere. So there is nothing to decompose. There is just one function. There is no like linking pairing. Everything is trivial. And then so some physicists started to study this using like ideas from this Chern-Simons theory and string theory. So they wrote this ZA, these like functions which Hikami already considered, or they have like their own physics definitions. So they wrote them as linear combinations of some other Q series which now have integral coefficients and also integral exponents up to some overall factor. And they call them homological blocks because it reminds them something from like conformal field theory, and they have the same. They have like a lot of kind of physics ideas how to define those invariants in a different way than it was done with the WRT. So those are the homological blocks, the ZA hat. This label A means these elements of this H group. Roughly, there is some. There are some complications, but roughly it means the elements of this group H, or spin C structures, abelian connections. Yeah, and the last thing I want to mention, of course, there was like so many other work on this Q series, but the last thing is 2018. These authors they kind of like did the same thing as Lawrence and Zagier, but for this more general setting. So even so maybe I'll just remind you this case. Yeah. So here this is like what they would call a homological block. So this thing which corresponds to WRT, and there is this second function which has no clear meaning, except that it gives you a modular form. So they kind of did this. Yeah, they found the other functions such that you get a modular form for many examples. So this was kind of like last step so far. Of course, they try to kind of categorize these invariants because they have integral coefficients, so they believe there is some homology theory. But this is not so important. So they found these vector-valued modular forms which correspond to as a component. Some of the components are these homological blocks. Okay. So here is the homological blocks definition. I didn't even write some things which are here on this formula. I just copied it from their paper. So but the idea is like this. So you have this three-manifold, which is given by this plumbing construction. So some surgery, using a graph. And if this graph has like 3 legs and it's star-shaped like this graph, you take the adjacency matrix. So it means that you just take a matrix where like you write like -2 for each of these vertices on diagonal, and then you write 1 if they meet, if there is an edge between them. So then you consider this like kind of like multi-dimensional Q series or theta function. So it looks like a lot like the Q series before, just that now we have like here is like a dot product of a vector with this matrix here. So So it's like we are summing over a lattice now, not just integers. Yeah, and then you add some like you have some additional variables, which you basically just integrate out. So it means that you just take some like some specific coefficient. Yeah, so basically there is this theta function and then something more going on. But this is like the formula which they got from like physics considerations, and yeah, so this gives you some Q series which they call homological blocks. Yeah, and now yeah.
Vortex means the vortex in thinking diagram.
Sorry.
What is the meaning of vortex?
Yeah, vertices means in the thinking diagram. Yes. Mm-hmm.
So I mean,
The-
you have
yeah.
this 3-leg star. I mean, so the 3-leg star-shaped graph means.
Yeah, it means exactly this. I mean, they also do something for 4 legs, but then it gets more complicated. So it's really like in general it's kind of in progress, yeah, because there is a lot more. You know, there are many like you can have like this thing, yeah, and yeah, they also consider it somehow, but like I think there are no like completely general formulas. So this, I'll now more talk about this 3D modality paper. So 5 authors. As in Poincaré sphere, as I told you, the authors were looking for representations of SL to Z, so like modular forms, such that the homological blocks are components of the corresponding vector of theta functions. Okay. So they constructed many examples for Plum manifolds. Using subrepresentation of this Weyl representation. So you have this Weyl representation for each integer m, which is just like that you take all the theta function for all residue classes, and then you can ask like maybe if I do some linear combinations of those, like there was this like theta 1 plus theta 11 plus theta 19 plus theta 29, etc. If you do some linear combination of those, you maybe get these homological blocks, which are invariants of this 3 manifold. Yeah, I mean, that's an important point, that if you take this formula, you can prove, they prove it in the paper, that it's actually a 3 manifold invariant. So it doesn't depend on the graph, on the way how you write your plumbing. Yeah. It doesn't depend on the way how you do the surgery. It only depends on the 3 manifold. So, yeah. So understanding the choice of the subrepresentation is kind of an open question in general. So they, in the end of the paper, they ask like, they kind of have a formula for this m, but it's not clear which subrepresentation to choose. Yeah, they do it. So if I understand correctly, they do it somehow that they first look at the homological blocks, they compute them, and then they just search for a good representation which fits the homological blocks. Yeah. So this is kind of the goal we are trying to do here, to find out which representation is the one which we want to take. So here comes like a definition, which is like very, I mean, there will be probably many changes to this definition. So if we take all the coefficients of these theta functions which occur in a natural basis of this subrepresentation, so this subrepresentation has some natural basis which they construct. So we take all the coefficients, I mean, I should say all the positive coefficients, and we call this modular spectrum. So it's done in a way such that we get this 1, 11, 19, 29, 7, 13, 17, 23, and we can divide all by 30, so such that we get the same thing as the Steinbring spectrum for E8, okay? So yeah, this is like a preliminary definition. So the only thing I want to say is that we care about these coefficients, which basically means the same thing that we care about what representation we take. Yeah, and then there is an important question: which of these coefficients actually correspond to homological blocks? So okay, so back to singularities. So now we have this E8. As I showed you, there is this relation of the coefficients of the Q series, or the exponents of the Q series, with the spectrum, the Steinbring spectrum of E8. So what could be the generalization for AN, DN, E6, E7, and then of course to other singularities. But this is like the first case to consider. Yeah. So it took me a while to realize this, because it took me a while to understand this paper, because it's written in a very different way. It's like a physics paper, right? So the theorem is like this. So if you have AD a singularity XP, and you take its link M, and you take the corresponding maximal abelian cover or universal abelian cover of this singularity, then the modular spectrum of M, meaning the coefficients of theta functions, is exactly the Steinbring spectrum of this abelian cover. Okay, so this is a theorem, and I mean the proof is kind of boring. Yeah, it's just like, you know, looking at the results of these 5 authors, looking at the theta functions, and examining example by example. So the theta functions were computed in this 3D modularity paper. So yeah, so there is the table. Okay, so I will just talk about each of these cases. So first of all, if we take AN singularity. So AN singularity, maybe I should write the equations, because or just like, I mean, AN is the simplest one, is the x to the power of n, and we have to add y squared plus z squared to get the surface singularity. So if you look at the link, it's pretty simple space. It's just this length space, yeah. So it means that, I mean, if this WRT or like homological blocks, so it was all computed for length space. It's kind of the, you know, easiest case. And if you do it, you get you actually get no theta functions there. Only thing you get there is some polynomial, yeah. And yeah, I should also say that, like, in all these cases, you sometimes not get like precise theta function. You get some like polynomial term, like, you know, like a monomial or something. And I think there is no understanding why is it happening. Yeah, maybe it's not important at all. It's hard to say. Yeah. So the important point is that there are no theta functions, and this nicely corresponds to the fact that if you like do the covering of AN, you get just C2, and C2 has no singular points here, because this is just like a cyclic quotient of C2 basically, and cyclic group is abelian. So so the spectrum, the Steinbring spectrum, is empty. Okay, so this is the first example. The second example is DN. For DN, you get this 3 manifold with 3 singular fibers, cipher manifold with 3 singular fibers, and the theta functions, like the positive ones, because there is always this negative part, are just theta 1, theta 2, theta n minus 1 for the number m n minus 2. Yeah, I'm not writing the m here as the second coefficient, but this is like the common. This is like the number. These are the residue classes modulo this number. Okay, and this corresponds to the fact that if we take the abelian cover, we get n minus 3, because we just have, you see here, like we have just 2 n minus 2, so we get like x squared plus y squared plus z n minus 2, which is n minus 3 singularity, right? And the spectrum is like this, so it fits the theta functions. And now we only have like 3 more cases. So the E8 case is very, very well known, right? Because this was done by Zagier and Lawrence, and we know that there is this spectrum. So this was the first example to consider, but then there was like a question how to generalize, and it confused me a lot that if we have E6, we kind of get D4, and I didn't know why. And the problem was that, like in E7 case, this was all. I mean, this all was all kind of already computed by Hikami, but he did not find the other theta functions to get the full modular forms. This was done by these five authors. Yeah. So he found only this thing and this thing, which looks kind of like a E6 spectrum, but there was something missing, and this is the other term you get when you do the full modular form. And also it's kind of nice that if you do this natural basis, which these authors construct, you get like a multiplicity here. You get this theta 3, you get it twice, and this nicely corresponds to the fact that there is a multiplicity in this spectrum. Okay, so this is the idea. So this is how. So yeah. And now, I mean, so you can ask, like, what happens if we do other singularities? Then you start having problems in the spectrum, because there will be suddenly some negative numbers, you know, because it's in the interval -1 to 2, and so this must be, I mean, this must be addressed, and this is not addressed in these papers at all. So they always kind of flip it to have it in the interval 0, 1, these coefficients of theta functions. But the same thing definitely works for all other Brieskorn homology spheres. Brieskorn homology spheres are of this form for P1, P2, P3 coprime. Yeah. So I mean, you may ask, like, of course I cannot, like, in general get the spectrum from the three manifold, because three manifold is just the topological information. There are counter examples that you cannot get the spectrum from the three manifold. But there is like work of Nemeti and others that actually, if you do spectrum only like modulo 2, then it seems that it's more like topological information than Hodge theoretical, and this is exactly what's happening for these theta functions. Yeah, these theta functions, they are considered modulo 2m, which if you divide by 2m, it's like modulo 2. So there might be some hope that you can actually, at least for some class of singularities, you can recover the spectrum just from these coefficients of these theta functions. Okay, so we are almost at the end. So the questions for the future is, so first of all, generalize to other surfaces in C3. So I told you that it's kind of clear for Brieskorn homology spheres, because it works really similar to the case of Lawrence-Zagier, except that there are these negative numbers which have to be addressed. But I mean, this was basically done in Hikami paper, and then the same thing in the Gukov. There is not much like a difference, and then there is a problem. So I kind of believe that this works at least for. So the next case kind of to address is these Arnold unimodal exceptional singularities. There is 14 of them, and they're like the second simplest, and I believe that this works at least for some of them. But even in Hikami paper, he kind of like computes WRT for all of them. But for one of them, he says something like, "Oh, I couldn't find a simpler expression for this," meaning the expression in terms of theta functions. So there are definitely some problems to find these theta functions and their coefficients, and also in the 3D modularity paper, they only consider like 5 of them of these 14. So their motivation is really different. So they show many examples, but they don't care about singularities. So they only show like 5 of these 14 singularities. So this is, I think, very interesting. And the important point is that there should be a role of this linking pairing there, yeah, which I kind of I ignore it here, because here I only consider this abelian cover, which is given by these 3 denominators. So there should be the role of the linking pairing. Why? Because in this 3D modularity paper, they give formula for this m, and this is like a least common multiple of these 3 denominators, which is kind of motivation why there should be like a spectrum of this singularity of this abelian cover. But then there is also some what they call contribution of abelian connections, which should have something to do with this abelian pairing, this linking pairing. So this is yeah, I mean, we should try to understand what's going on here. And so then the other question is like, we have this the full modular form, and then we have some components which correspond to homological blocks. So we may ask like, which elements of the spectrum correspond to these homological blocks. So partial answer is, if we take these Brieskorn homology spheres, then there is this action on spectrum of Z2 to 2, so it's always like 4 tuples of elements of spectrum. But among them there is this least element, which is kind of nice. So the least element corresponds to this. In the case of homology spheres, there is only one homological block, and it corresponds to the least number in the spectrum. Yeah, and then of course the most important question is like, what is the conceptual explanation of this like kind of surprising relation? Because here we have like very complicated three-manifold invariants, and it seems that they are related to Steenbrink spectrum, but of a different singularity. So I mean, we should ask if there is something deeper hidden in it. Yeah. So I hope there will be more in future talks. So are there any questions? Of the H1?
Yeah, no. I mean, spectrum question.
Yeah. Like, what is the meaning like of the the Hodge theorem? Or yeah, I mean, to be honest, I have no idea. It's really like I'm kind of looking at these numbers and I see they're the same. But that's exactly like a good question. Yeah, what does it have something to do with Hodge theory? Yeah. Okay. Yeah, I mean, as far as I know, it's really like a kind of surprising for most of people. Well, okay, so if there are no questions, then thank you.